Okay, class, so today we're going to take a look at differentiation in the tangent line, and I'm going to introduce derivatives, which is one of the most important concepts in calculus. It's actually what most of our lessons in the future will be based on. So what are these words that Miss Sal is speaking about? Well, here's a few things that we're going to take a look at, and one of the words is differentiation. Differentiation is actually the term used when we're asking you to find a derivative. So I can state find the derivative, or I can say differentiate the function, right? And the other hand, derivative is the result of differentiation. Okay. Now, what is this derivative that Miss Al is speaking about? So let's take a look at it in the real world context. And the derivative is actually how a function is changing in time. So it is a rate of change, just like let's take acceleration, right? People say, well, that's how fast you're going. Well, actually, no. Acceleration is how fast is your velocity changing in time, right? So you've probably seen that in physics, so you're going to see that in physics. We've also seen a rate because rates are slopes, right? Well, the derivative, once again, is a specific kind of slope, and it's the slope of a tangent line of a function. So just to recall, the slope of the line is equal to y2 minus y1 over x2 minus x1. And in order to find the slope, you need to have 2 points so that I can see an actual change between the 2 points. And just some new notation for you. We are going to be seeing a symbol that has an f apostrophe x. It's pronounced f prime of x, and it's stating that this is a derivative. Another way to write a derivative, or the symbols for derivative, is dy dx. It's pronounced dy dx. And this is another way of writing a derivative. So let's continue on to the tangent line problem. So what I'm going to do is kind of show you how we can take a look at slopes of lines to figure out what it means to have a derivative. So let's, for instance, take these two dots, right? Like we said, I can find the slope of the line, but as long as I have 2 points. So in order to do that, I can take these 2 points and find its slope by connecting the dots. Well, this is actually called the secant line. So anytime I draw a graph and I take 2 points and I connect the dots between them, I've created a secant line. And so what tends to happen is, here is one of your markers for an x. So let me just pick a pen real quickly. I have an x right here, and I have an x right here, right? Well, like we said before, in order to look at a slope, I need the 2 y's and the 2 x's. So what you'll notice is this entire section is a change in x, right? So I can write this as change in x, and this entire section right here is your change in y. That's how we may write it as. Well, what the tangent line problem is doing is saying, okay, well, I can find the slope, but what happens as I move these dots closer together? So, oops, sorry. Let me take this line. I'm going to move it down a little. I'm going to take this line and say I'm going to move this dot right here. Well, if I do that and I connect the dots, does the slope of your secant line change, or does it remain the same? Well, as you can see, initially, I used to be here to here, and that to here, oops, my mistake, let me draw that again. I used to be at about here. Well, when my line was connected there, I had a different slope to this line. However, as I get closer, the slope of the line tends to change. Well, so then we're probably thinking, okay, well, what's the point of this, Miss Sal? What's going on right here? Well, the tangent line, the derivative is a tangent at a specific point. So what we're trying to do is find out what is the slope, but what happens as my points get closer and closer and closer and closer and closer together. How do I kind of analyze that? And so if I'm getting closer and closer together, what is my delta x going to approach? Well, you're correct. Delta x is going to go towards the number 0, right? So just to take a look at this, here is the equation for the slope of a secant line, right here. So slope of secant line is right here. And it's taking the same exact format that we had before. I have my first point right here, I have my second point right here, and I have the change right here. So what we're going to do is take this one step further and take a look at its derivative. So here is the formal definition of a derivative. And I'm going to use my pen so we can follow along. But if you take a look at this, f prime of x is the same as when the limit of delta x approaches 0. So the limit of delta x approaches 0, delta y over delta x, which is the same as the slope. But instead, I'm going to use this function notation right here. Right? So the slope of the function f of x for all values of x has to follow this equation. And you've actually seen this equation when we were doing limits for one of your homework assignments. So let's actually try and solve one of these problems and see what we get. Okay. So let's, I'm going to move this away for now and we'll get back to that later on. But I want to take a look at this first function right here. F of x is equal to 2x squared minus x, and it says use the derivative of the function by using the definition of a derivative. So what I'm going to do is I'm going to take this equation and use it to solve for f prime of x. So according to this, f prime of x is equal to the limit as delta x approaches 0, f of x plus delta x, close parentheses, minus f of x, all over delta x, right? Okay, so I'm going to move this down if you guys don't mind. I'm going to extend my page. So what I'm going to do then is plug things in. I'm going to want to plug this function of x delta x into this piece right here. So what we'll do is we're going to take this piece and start plugging in my x plus delta x. So this is equal to 2 times, and like I said, now the first one says plug in x plus delta x, close parentheses, squared, minus, once again, I have another x, so I have to do x plus delta x, close parentheses, and then my next function says, well, I need to minus f of x. So here, I'm going to minus f of x, which according to this is 2x squared minus x. Okay. And I'm going to put all of this over delta x. Okay? So, if we continue, what I'm going to do now is, right now I have so many terms I need to distribute and hopefully get a simpler term. So if we were to solve this, I get 2 times x squared plus 2x delta x plus delta x squared. So I do want to clarify, delta x is different from x. Look at them as two separate variables, okay? And so I'm going to get rid of those parentheses and I get minus x minus delta x. And again, get rid of the parentheses, minus 2x squared plus x, right? This all over delta x. And once again, if you take a look at this, I still have a set of parentheses, so I'm going to distribute that, and I get 2x squared plus 4x delta x plus 2 delta x squared minus x minus delta x minus 2x squared plus x all over delta x. So I was saying that we need to make things simpler. Well, right now it doesn't look so simple, but if we start to collect our like terms, this minus x, let me use another color, this minus x is going to cancel out with this plus x. This 2x squared is going to cancel out with this negative 2x squared. And what I have left is 4x delta x plus 2 delta x squared minus delta x all over delta x. Well, am I finished? No, because if you remember, I'm not just solving and simplifying this. I need the limit as delta x approaches 0. So what number should I plug in every time I see a delta x? Good, 0. Well, if you notice, if I plug in a 0 here, a 0 here, a 0 here, and a 0 here, I'm going to get 0 over 0. Well, from our last lesson, our last chapter, what do you have to do if you get 0 over 0? Good. I have to factor something. So if I were to factor this out and I take a look at my numerator, there's a delta x here, a delta x here, and a delta x here. So I'm going to just pull out that delta x. So let me continue this, and I'm going to pull out delta x. And if I factor this, I get 4x plus 2 delta x minus 1 divided by delta x. So like we said, when you factor and you have indeterminate form of 0 over 0, what's one of the things that you're looking to do? Good. I'm hoping you said cancel, and that's exactly what happens to my delta x's. And so now, all I need to do is complete the problem by once again plugging in 0 every time I have a delta x. So I have 4x plus 2 times 0 minus 1. And if I solve this, this 2 times 0 is going to cancel. And so f prime of x, which is the same as the limit as delta x approaches 0, right, of the function, I'll just say f of x right here, is actually equal to 4x minus 1. And there you go. Your derivative is equal to 4x minus 1. Okay? So limits are not going to go away. Like I said, it's going to be seen throughout this chapter. And this is one example of how we can find these different limits. I'm sorry, not limits, but different derivatives. Alright, and that's the end of video 1. And I'll be continuing a couple more problems in the next video. Thank you.